Hi, everybody. Welcome back for day 5 of our Python course. I hope that everything is moving along well for you and that you are understanding the pieces that we've been doing all along the way. Today, we're going to take a step in a really different direction than we have previously. As you know, along the way, we've been trying to build a FASTA database sniffer, something that will read an arbitrary FASTA database, come back with a list of, or a count of how many accessions appear within it, how many protein sequences, and also tell us about the sequence composition of that whole database. So how many times we had a C in a sequence, or an A in a sequence, or an L in a sequence. So today I'm working on a borrowed laptop. Thank you for the loan. And we will get through today's lesson, and then hopefully this recording will show up just fine on the net soon thereafter. Okay, I want to point out that our code has gone through another big shift. I had a little bit of help this week. I hope you don't mind. I got one of my bar plots working just fine, but then I ran into barriers on a couple of the others. So I called in some help from Peter Van Heusden. Oh, sorry, Heusden. What? Heusden. Oh my goodness, I wouldn't have thought that one. Well, he's over at the University of the Western Cape, and I have to say, he's one of the better trainers around in the space of Python. So if you want a more comprehensive course, I would definitely check in with him, and he's over in Sandby at UWC, because from time to time he offers a more complete Python course than what this one is. So this is a good taster to help you get introduced to some of the things you can do without a lot of programming experience. Okay. So I have opened my Python code in a web browser instead, so I don't have all of my little colors showing up, but maybe that makes it easier to read. You can see that we've added to our import set up here at the top. Previously we had sys because we wanted to look through what had been passed to our script by the user on the command line, and we needed sys to do that. On our most recent class, we added collections to this, because collections offered the counter object that we were going to use to count how many times each amino acid appeared. But you can see that today we've added matplotlib.pyplot. And as you noticed in the emails that I sent around today, matplotlib is not included by default when you install Python, which means that you had to go through an installation process to make that library available for this import command. Now, if you just ran this import command without having done the install of matplotlib, you probably would have received an exception. See, if we were being proper coders, instead of just having import matplotlib in here, we would have surrounded that with a try and catch, because then we could catch the exception and we could tell the user, no, you need to install matplotlib before you can run this code. That would be a polite thing to do, because otherwise somebody may try to run this code and get an unfriendly error instead. Okay, so we're being a little impolite in that matplotlib is going to be something that we require for our code to work, but we're not going to tell the user in any sort of friendly way. I've updated our version number to version 0.4, and basically nothing changes through this section. You can see we still have our collections.Counter object right here to accumulate our letters. I wanted to ask you a question about this if-else structure right here. So when we look at this structure, I want to ask you, what happens to the letters in the descriptions of the protein? Remember that when you have an accession on an accession line within the FASTA database, it has an accession for what this protein is named, but then there's like a space or a tab, and there's this descriptive text there. Do you remember seeing that? So what happens to those letters? Are we going to allow those descriptive letters to affect the overall sequence composition that we see in our count? We don't want to, do we? Right? So how are we preventing the letters of the description, or of the accession number for that matter, being counted like sequence letters? Can anyone see how that happens here?
It skips everything that's after the accession line, so it doesn't and goes on to the next line. It starts reading from there.
It does, but by what mechanism in the code does it know to ignore the description letters in making those counts? Does everyone remember back to lecture number 2 on conditional execution? In conditional execution, you have 2 code paths. Here we have one that adds to the accession count, but the alternative is that we update our letter counts. So this if says if it's an accession line, one that starts with a greater than symbol, just add to the count, but ignore all the other letters in there. It doesn't do anything with them. It's only in the case of this else, if the first character is not a greater than symbol, then it will go ahead and add those letters to the counts. So I wanted everyone to think about that. You know, if we had simply told it every line of this FASTA file, add it to letter counts, we would have letter counts that reflected not only the sequence, but also the descriptions. So it's important that we had this else in there to affect that. Okay, we decided it was important to close the file, but I've added something really new right here. And I can explain it pretty succinctly. There was a bug in the code that I gave you on Friday. Because one of the things that happens is that Python counts the last character of a line, which is a new line character saying go on to the next line. And that new line character does not have anything to do with sequence. It's just a break separating this line of sequence from the next line of sequence. So we needed to drop that. You can see here that I've added a delete letter counts, and here I've got a single character. I want you to note I'm not using double quotes, I'm using just single quotes. And in this case it's because I'm giving a single character the new line character. Now the new line character we haven't really talked about very much in this class, and I discuss it when I'm teaching people about ASCII, but I haven't mentioned it here. It might be obvious how you would check if a letter were the letter A, or if the letter B were there, right? You would just say in our code up here we gave an example of that, right? If the first character is equal to a greater than symbol. But down here I am using a new line character, and you can see that this single character is represented by 2 characters. So typically in programming languages, when we're talking about a few special characters, most typically new lines and tab characters, we use this backslash notation. Right? If you were checking to see if somebody had pressed the tab key, you can't say if their input equals tab key, right? Because the tab will just introduce this white space in your text. So when we make reference to tab in a comparison like this, we would, or in a function call like this, we would use \t. But in the case of go to the next line, we call that \n. So whenever you see \t and \n, I want you to think about that one of these is a white space tab character, and \n means go to the next line. I noticed this bug because of the visualization work that we're doing today. So I'm going to simply run the code as it is in our first go. But I wanted to mention that, and this part I appreciate won't appear on your screen very clearly at all, we needed to install the matplotlib library. And so behind the scenes, we have run Python with -m pip, which is to specify run its software updater and improver here. And we're going to use the operation install, and we're going to make this library available to this user only. And the library of choice is matplotlib. And so what the software has now done is to download each of these WHL files and install it into the database here so that Python will have access to it. And we see that in this case, although we told it just install matplotlib, that it installed a whole collection of packages: 6, Cycler, Kiwi Solver, NumPy, PyParsing, Python DateUtil, and Matplotlib. So all of those are necessary for the installation of just Matplotlib. Now I'm going to change over to this other window where hopefully the fonts are a little bigger and people will be able to see things. So in this case, I want to run the script that we have for today. So that's Python 20190520 goal4pi. And I'm going to go ahead to give it the name of the Mycobacterium database as well. MY, there it is. Okay, so I'm simply going to run the code exactly as it is. It's going to take a moment to think about things. It's reflecting on all its sins for being a Windows computer. Does that always happen? There it is. We have motion again. It may be that the first time after running the install, it does all this other business. Well, you can see I've been doing a little bit of coding work back there, right? Now we have a graph showing up. The whole point of today is to learn how to create bar plots from within Python. So I wanted to show you that our counter in the back is still reporting these values. If we had run this without that line in there, without deleting out the new line character, it would also be telling us how many new line characters that it had generated as it sniffed through this entire FASTA database. Okay, you can see that the software hasn't finished running, though. It didn't pop me back to a command prompt down here. And the reason for that is that we have this bar plot up here. And as you can see by these little coordinates at the bottom right, it's watching what we do as we move around with the mouse. If I click out of this graph, you can see that it pops up yet another graph. And finally, a third graph. So that's the big change for the code today, and we can walk through how that happens. So I've already mentioned that we needed to drop the new line character. That's the letter counts thing is keeping just a count of how many times new line is there. Here we just tell it to delete it from there. Now, is there another way that we could have avoided new line characters from being added to the letter counts in the first place? Yes? No? Does it sound impossible? How could we have avoided the software dumping these new line characters into the counter? I'm going to scroll up a little bit. Under what conditions do we push letters into the counter? We just talked about this. What's the one condition that a line from the FASTA is updating our frequency counts? They're not on a accession line, right? We already said descriptions don't go in. So we have our if up here about that. So it is possible that within this loop where we loop through each letter on the line, that we could say, so long as this character is not a new line, dump it into the letter counter. That would have been fine, right? So we could say if it is a new line character, do nothing. If it is not a new line character, go ahead and put it into the frequency counts. So that's one way we could have dealt with it. But I was a little sloppier. I went ahead to allow it to be in the letter counter, but here I just deleted it out of that little dictionary. Okay. Now, we have some functions available to us in this counter object that are going to help us out quite a lot. So one of them is this most common function, well, actually method. Why do I call that a method rather than a function? As you probably recall back to the second lecture, if you see a dot in front of what looks like a function, it usually means that that function is actually a method. It belongs to this class. So I can't use a most common function on just anything, but I can use a most common method if what I have is a counter. Let's take a quick look at how that would play out. Oops, I'm going to move back here. I'm going to just start Python by itself for a moment here. So I'm going to I'm going to just create a collections again, import collections. And now I want to make, I'm going to create a variable called, well, I'll use lowercase, ctr is equal to counter, and now I'm going to feed it abracadabra. Oh, what happened there? I imported collections, but it doesn't recognize it because I haven't specified that I wanted the counter object out of collections. Okay, so I'm going to say counter is a counter object drawn from collections, and I'm going to create it with abracadabra. Nothing happens. But we did create a new object, ctr. Now what on earth is that? Right. So when we created the counter object, it was initialized with a string, and when it is given a string, it says, okay, how many times does each letter appear in the string? So I can see that abracadabra contains 5 A's, 2 B's, 2 R's, 1 C, and 1 D. Now, what do we notice that's kind of odd about the ordering of this counter? Yeah, I'm going to hit some enters here so it goes up higher on the screen. It's not in alphabetical order. So the software knows that letters have a particular ordering, but in this case, the counter was created in a way that it decides the order of letters within this dictionary it's creating based on the string itself. So in abracadabra, A is first, B is second, R is third, A is fourth, but we note that it doesn't have to create the A when it hits the second one. It just adds another count to an existing A. So the C shows up after it. So the first 4 letters should be A, B, R, C. And down here we see A, B, R, C. So even though the software knows these letters have a structure, it's actually going to add them in the order that they appear in the string. So we've now created a counter object. Let's try this new function that I've just explained from down here, most common. So we're going to run the most common method of CTR. And we can see that our output has changed a little bit. I'll raise that up on screen again. So now we see that that A and B and C, actually it's just the same, isn't it? That's awkward. Well, but there is one change that's come out of this. Before, it was calling this a counter object when we told it to simply print the result of counter. But when we ran the most common thing, it no longer reports that it's a counter. Isn't that odd? So I'm going to repeat that last command, and this time I'm going to capture the result. I'll just say result equals counter most common. Now we can use commands like type, to ask what is the type of counter, and here we see that it correctly reports that this is an item of type collections.Counter. But what about that result that came out of it when we told it to sort by most common? Type result. Do you see what's odd here? When you tell a counter to report its most common entries, it does not give you a counter in reply. Instead, it will give you a list, and a list is a different type. So when we work with our frequencies from the FASTA database, knowing how many of each letter in the order they were first encountered by the software is fine, I guess. But we'd really rather know things like what is the ordering of amino acids by popularity in this database, or alternately, alphabetically, what are the entries in this database. So what we're going to do then is have 3 different plots from exactly the same numbers. In the first case, we can ask what is the native ordering of the counter that includes all of the amino acids of this database. In the second case, we can ask what is the ordering of amino acids in this database from most common to least common? And thirdly, what is the alphabetical ordering of these amino acids? This is going to require that we work with some different data types, though, and we've already encountered two of them, the counter and the list. Okay, so the frequency list is going to grab all of the amino acids seen by the counter object in order of their frequencies, from most to least. We are also going to create an alphabetical sort of these. So in this case, we need to get the letter counts out, but we're going to sort them based on their key names, on the letter that it found, the letter associated with each amino acid. And then we're going to give that to a dictionary, create a dictionary from it. So if I were to say sorted counter, sorry. Okay. So you can see that in this uppercase, I've already scrolled it off screen. Let me move back by one. If we use the most common method from this counter object, we get back this list. We can capture that list. But down below, we're doing something different. We are instead running the sorted function on the items within counter. And you can see that in this case, it has reordered the list, not so they appear in the order they appear in Abracadabra, but rather in the alphabetical ordering of what are sometimes called the keys of A and B and C and D and R, all the distinct letters of Abracadabra. So Python is able to manipulate the data within this counter object in a variety of ways. And which function you use is going to change what type of object comes back from it. So if we were to capture this sorted list in something called alpha equals sorted, what type is going to come back for that? If I type that. All right, so here we see that running type on alpha gives us a list. But if I want to store that in, if I take the list that came back from doing this in dict, I now get a dictionary class back. Okay, so what the heck is going on here? I had one counter, and suddenly I've turned it into lists and dictionaries. What's a dictionary? It turns out that counters and dictionaries have a lot in common. You can see that in each case they have a key and they have a value. In fact, a counter is what we call a subclass of dictionary. It's a dictionary that has particular functions devoted to counting frequencies. You wouldn't do that with all dictionaries, but having the same functions within dictionary in the counter helps us a lot. Okay, so I feel like I'm talking myself right into mud here. We have a class, the counter, that does all the counting for us. When we apply particular sorts, that gets us into different data structures that are either called dicts for dictionary or list. All right, so why is that valuable to us? It's because we're going to produce 3 different kinds of plots, all from the same counter data. So in the first case, we create a graph that represents the counter itself. So how much work do we have to do to produce that on-screen bar graph? The answer is not very much. As I mentioned, every dictionary is going to have keys and values for those keys. In this case, each key in the counter refers to a particular amino acid. Every value represents the number of times that key appeared in the strings. So when we run matplotlib.pyplot.bar, we are operating a method to construct an on-screen bar graph from the information that we feed it. So when you create a bar plot in this matplotlib code, you need to provide it a name for each of the bars that it's going to output, and you need to provide a height for each bar. That's not such an unusual kind of expectation, right? So here we tell it that the key values can be found inside keys of letter counts. That's the counter object that we initially created. And we also are giving it the bar heights as letter counts.values. Now there are lots of other things you can feed to this method, right? You could provide it the axis labels. You could provide it things like a main text to appear over the graph. But I was really focusing as much as I could on simple ways to produce that bar plot. So we're not, for example, making use of the arange function built into NumPy and so on to do a bunch of advanced stuff. In this case, I just wanted you to see a relatively simple call to create a bar graph based on these counts we've already generated. And then the next line, I think, is pretty straightforward. Here we're going to call the method show on this Python plot to actually visualize this graph that we see on screen. Anything too weird so far? I have to say, putting dicts and counters and lists is not on the quiz, right? In fact, there is no quiz. I'm just grateful you all are here. Thank you. All right. So that wasn't so bad. Having created a counter, which I think everyone was able to follow pretty well, we were able to create a bar graph with one line of code and then just display it with another. So that's pretty easy. Things get a little weirder as we get to this next one. So remember that we also had a frequency list. We derived this from the counter, and that frequency list was a little harder to interpret. That was more like this sorted thing up here. So when we, let me see, that's, oh, sorry. I've got the wrong line of code in front of me. You remember when we ran most common, that gave us back a list that looked like this, sorted by the most frequent to the least frequent. A list is not a dictionary. A list, in this case, has an item that represents the letter A coupled with a 5, the letter B coupled with a 2, the letter R coupled with a 2, etc. And so it doesn't have keys and values. They're not named keys and values within the list structure. That was a little unfortunate, and frankly, I was quite puzzled on how to make that result visible in a plot. So this was code produced by Peter over at UWC, who gave me back a command that I found kind of puzzling when I first glanced at it. So you can see that in this case, we're going through a string like this one, a list like this one, and we're foring our way through it. So if I were to say, for thingy in result, oh, I gotta go tab in one here, print thingy. You see what happened? So the software sees that thingy in this case, that this result contains 5 thingies, and the first thingy was A, 5. The second thingy was B, 2, R, 2, and so on. So the software is able to recognize that these thingies. Let me see. Is thingy still defined? It is. How helpful! It's the last one from the for loop. What is the type of thingy? It's a tuple. Tuples are yet another way to describe lists of things. But the useful thing is that each of these thingies can be, we can speak to individual elements of it. So thingy 0, square bracket, is D. Thingy 1 is 1. Okay, so let's work out how this worked. We started with a counter. We dumped its result into a list. And that list had a structure very much like result here. We're now going to split that list up into different thingies, tuples in this case, and each tuple we're going to separate into 2 elements, the 0th one and the first one. So in this case, this is what one of those thingies look like. Thingy 0 is the D, thingy 1 is the 1. So in the same way, we're going to have amino acids and the number of counts that this thing appeared in the database, and we're going to decompose that to make our bar plot. Bizarre, but this is this is the way it worked. So in this case, we're going to call for the 0th element of a thingy, where the thingy is cycling through each of the frequency list items. And in this case, we're going to grab the first element rather than the 0th of it after doing the same for loop. So we're feeding our parameters by way of for loop. It's just kind of an odd way to do it, not a way that I would think of doing it, but if you're an experienced Python programmer, this probably seems perfectly natural. Different strokes for different folks. I'm a Java programmer, we're a little weird. Okay. So we can see that in the first case, we pass it the result of the keys method and the values method. In the second case, we're passing it the list of letters followed by the list of values using these for loops. Crazy. And finally, we want to be able to show the alphabetically sorted list. Now, where did alpha dict come from? I'm going to roll back up here. Alpha dict is right here. You can see that we had letter counts, the counter, report its items. We sorted that information on key, on the amino acid symbol, and then we dumped that into the constructor for dictionary, which gave us a dictionary object called alphadict. Now, what did I say about the relationship between dicts and counters? Counters are a subclass of dictionary objects, which means that they have a lot of methods shared in common. So you can see that in this case, we can pass the keys structure of alphadict just exactly the same way as we did up here, because they share this keys and values pair of methods. So we don't really have to know anything new in order to do the alphabetical list on top of the direct counter list. All right, so I'm going to exit this, and I'm going to rerun the code, and this time we can try to look for anything odd that appears. It's going to take us time to think about this one. Okay, it's found the Mycobacterium tuberculosis database. Okay, so what it's visualizing up top relates directly to what we see down here. It's an object of counter type. It has values like A, 177,317, G, 133,377, and yet what is showing up on screen is different than that. So why is, here we're not applying any ordering, we're simply having the counter object return strings, return the letters in the order they were added to the dictionary. So if we are to open the first sequence from the Mycobacterium tuberculosis database, I'm going to tell you right now, M is the first amino acid in the first protein. T may be the second, but it could be that the first sequence starts with MMT. That could happen. But in any case, T, threonine, is the second amino acid, the second distinct amino acid that it observes as it processes through those sequence letters. This ordering doesn't make much sense, does it? This is why I decided we shouldn't just visualize counter as it is. It's really better for us if we show counter sorted the way we want it to be. So I'm going to close out figure 1, and up pops figure 2. So remember, figure 2 is not a counter. We can see by this square bracket notation here that what we're passing it is a list. So we can, here we see that the most frequently observed letter in the amino acid database was 177,317. That looks about right, doesn't it? So the software is doing a lot automatically for us. It's decided that bars should be separated from each other. It's decided that bars should be blue. It's decided that the label should appear right here in the middle of each bar. It has decided what gradation should be on this scale. it is possible to tell the software to do things like use a log scale. In this case, we're not doing so. So I hope you don't mind, but I'm going to ask you a biological question about this image. Is the amino acid composition of Mycobacterium tuberculosis, is it weird? Do you see anything that seems strange to you in this list of amino acids? First off, did you expect that amino acids are used more or less uniformly among protein sequences? They are not. They definitely are not. So one of your first clues for that would be to look at the genetic code. Some of the amino acids have just 2 codons or 1 codon for them, whereas others have 6. Right? So that's already a clue that biology has a greater random chance of incorporating some letters than others. Did you think that it would be this distorted between most common and least common? I would have expected to see leucine or isoleucine at the top of the list. But in fact, alanine was the most common amino acid across Mycobacterium tuberculosis. That was a surprise for me. I didn't know that till today. But I would point out that these last 3 are almost always the last 3. Methionine, tryptophan, and cysteine are always, essentially always, the last 3 amino acids by frequency in almost any species you could look at. So C, W, and M are always going to be trailing the list of everything else. Okay. Well, so we got a little bit of biology out of sniffing the database. But remember, the way we created this graph was different. This is the one that's got that pair of for loops in the way it passes in the keys, which appear down here along the bottom of the graph, and the values, which are reflected by the bar heights. And never forget that although we've used a very simple call, we really could decorate that with all kinds of other things. Maybe we wanted the bars to be magenta, did you say? Magenta? Maroon. We could go for maroon. There's an HTML code for that, I'm sure. So yes, it is possible to customize this quite a lot. We just haven't done so in this case. All right. Now, for the last case, we have again not, we had a counter object in the first case, a list in the second case, and a dictionary in the third case. And you can see that in this case, the sorting on the basis of the keys has taken place. So this graph is not as aesthetically pleasing, I think, as the frequency plot. And one of the reasons is that the very largest value, alanine, is right next door to the very lowest value, cysteine. So you end up with this big gap tooth right here between among the first three amino acids. So that's a little awkward, but there it is. Okay, and finally, if you close this out, if the mouse will let me, there we are. You can see we're out again. So I've done a couple things to make the output a little cleaner. I added a blank line after the protein count up here. And don't forget, we still have all done down here. One of the other effects of adding the output of these bar plots is that we can now double-click on the software to launch it, except for one thing, that the software is still expecting us to provide a value on the command line. So I guess that's not going to work after all. But if we were to have double-clicked, if we had hard-coded the FASTA file name, then the software would not have simply dumped its output and then jumped off of screen again. It would have paused because we had those graphs to look at before the software could complete. Okay, so we've done a little bit of a jumble today. We've been looking at the matplotlib, which is a very handy way, very quick way to get a graph generated representing, in this case, frequency counts. But you can do things like XY plots quite easily with this as well. We've talked about the relationship between classes, well, in this case, a class and its subclass, which is to say dictionary and counter, which is a subclass of it. And we also talked about lists. I realize that some of that stuff may seem like quite a jumble if you've never really encountered them before. But this is something that's going to happen in programming. From time to time, you're going to be working with a data structure you're not that familiar with, and figuring out how to deal with its oddities to get the visualization you want out matters. Okay, with that though, I think we're all done with part 5. When we get back together on Wednesday, our very last session, we're going to look at a library that is characteristic of bioinformatics for Python users. It's a toolkit that includes an awful lot of classes and functions and methods that are useful anytime you're doing sequence analysis. So I hope to show you kind of an easier way to get at the contents of common file formats like FASTA that don't require so much of a roll your own methodology where you have to create your own readers and so on for formats. So I look forward to that, but I will see you again on Wednesday at 3. Thank you.